continue with our discussion on quantization of electromagnetic fields. So, do you have any questions of the derivation and the discussion that we had last class? So, let me recall what we are trying to do is starting from Maxwell's equations, deriving an expression for the Hamiltonian, the total energy of the electromagnetic field. And what we did was we wrote the equation in terms of vector potential, the wave equation in terms of vector potential, because knowing the vector potential, I can calculate the electric field, which is minus del I by del T, and the magnetic field, which is del cross A. And so, if I get the solution in terms of vector potential, I can calculate the electric field, magnetic field, Poynting vector, energy density, everything. So, we wrote down the wave equation for the vector potential, and we use separation of variables technique to get solutions in terms of plane waves, exponential ik dot r minus omega t. So, now in normal free space, all frequencies are allowed, all directional propagations are allowed. So, the total electromagnetic field would be an integral over all possible solutions. Now, instead of dealing with integrals, it is much easier to deal with summations, and at the end, we will let the space go to infinity. And so, what we did was, we said that let me consider a cubic volume of side L. And we apply what are called as periodic boundary conditions. That means I say that the field on the plane x is equal to 0 must be equal to the field on the plane x is equal to L. It doesn't tell me that the field is 0. It's whatever the field at x is equal to L is the same as field at x is equal to 0. Similarly for the y coordinates and similarly for the z coordinates. So, I have a volume of space of cube L, which is such that it repeats again and again. So, the field on the plane x is equal to L and x is equal to 0 are exactly the same, and similarly for the y and z coordinates, and this is called a periodic boundary condition, and this does not restrict the field to within this volume. The field is going outside also. The fields are traveling waves. All I am requiring it, the field here and here must be the same. This is different from a condition which people can use, in which I say that I consider an enclosed cavity of side L, and I say that the field is completely confined within this cavity. Then I will apply boundary conditions saying the field here has to be 0, field here has to be 0. That will give me another set of modes called standing wave modes, and these are modes which are called propagating wave modes, because these are solutions in terms of propagating waves, and the solution, if you have a box which is which has perfect reflecting walls, that will give you standing wave solutions within the cavity. So, we are using the propagating wave solutions, and we say that the field at x is equal to 0 and x is equal to L must be the same, and similarly for y and z. And what we find is, because of this condition, the frequencies get discretized. The kx, ky, kz, which are the components of the k vector, get discretized, and we get a discrete spectrum rather than a continuous spectrum. So, remember we found that we had the kx must be equal to 2 pi by L into nx. And the propagation constant is k dot k, which is equal to kx square plus ky square plus kz square is equal to omega square by c square. And because kx, ky, kz are discretized, omega is also discretized. Not all frequencies are possible, only those frequencies which are satisfying these conditions are allowed. So, the modes now consist, these are the different modes of the electromagnetic field with these boundary conditions. And the total solution is a sum of all the possible modes. And so, we wrote, for example, the vector potential A as sigma E lambda, lambda is equal to minus infinity to plus infinity, into q lambda exponential I k lambda dot r minus omega lambda t plus q lambda star exponential minus I k lambda dot r minus omega lambda t. And lambda is a subscript which is a short form for all this nx, ny, and z, and also the polarization states. So one mode is characterized by one value of nx, ny, and z, and one polarization state. And because divergence A has to be 0, k dot A is 0. So for a given vector direction k lambda, I can have two independent polarization states, which we can choose as two linearly polarized states or two circularly polarized states. That is in my choice, right? So here, for example, I can choose linearly polarized states. So if my propagation direction is like this, I can have one polarization like this, another polarization like this. These are two independent modes. So for every value of a set nx, ny, nz, and e, I have a mode, and these modes are orthonormal to each other. They are independent. They are orthonormal. They are orthogonal. That means they are, as I showed you, the integral between two different values of lambda corresponding to a vector are 0. So actually, I can also write, we will later on also be able to write like this in this form, in which I absorb the time dependence within the Q. So I can also write like this: E lambda, Q lambda of time exponential I, K lambda dot R plus Q lambda star of time exponential minus I, K lambda dot R. Where I've absorbed the time dependence. The time dependence is contained in this coefficient Q lambda. It has the amplitude and the time dependence. The amplitude is just the Q lambda, and there is a time dependence which is classically exponential minus I omega lambda t and exponential I omega lambda t here. Because later on we will see that in Heisenberg picture, the operators will be time dependent, and these actually become operators, and they will carry the time dependence. The Schrodinger picture will correspond to, by just putting t is equal to 0, and time independent operators they will become. So I will make this clear as we proceed. Okay, so once we have got a vector, we can actually calculate E vector minus del A by del T, and H vector 1 by mu naught curl A. So we did this calculation last time, and finally we obtained an expression for the Hamiltonian, the total energy. Please note this is an H without the vector sign. This is the magnetic field here, and this is the total energy Hamiltonian, which we remember we had got this expression omega lambda square Q lambda star plus Q lambda star Q lambda. Which is actually in classical, there is no problem. In the classical picture, I can write this as omega lambda square Q lambda star. So remember what we did last time. We calculated the electric field, calculated the magnetic field, then calculated the total energy, which is integral over the volume of half epsilon 0 E dot E plus half mu 0 H dot H. So I left those simplifications to you. You have to use the orthogonal condition between the exponential factors here, and you will find that finally the expression for the Hamiltonian reduces to this quadrant. Now, what I want to do is, okay, so this is still classical. Please remember this discrete values of omega I am getting is a classical, because of a classical boundary conditions. There is no quantization here yet. We are still in a completely classical picture. So if I make the length go to infinity, the spectrum will become continuous. Because remember, these are different values of kx differ by 2 pi by L. And as L tends to infinity, these will become continuum. All values of kx, ky, kz will be allowed. All values of frequencies are allowed, etc. So these different values of lambda, this summation is coming because of the boundary conditions, periodic boundary conditions we have applied, and this is a sum of the terms like omega lambda square, q lambda star. Now I want to quantize this problem. For that, I need to write the Hamiltonian in terms of canonical conjugates, conjugate variables. Just like we did for the harmonic oscillator, you have to write it in a form which satisfy, in which I find pairs of canonically conjugate variables which satisfy the Hamilton's equations of motion. Yeah?
What are exactly the conjugate variables, I mean, whose commutation is non-zero?
No, which satisfy the Hamilton's equations of motion. Which satisfy the Hamilton's equations of motion. That is the classical picture, classical mechanics. And the Poisson bracket, I can calculate the Poisson bracket in classical mechanics, and I replace the Poisson bracket by a commutator bracket to quantize.
Multiplied by IH cross.
Yes, yes. So this again will become clear because I want to put this in a form which looks like a sum of harmonic oscillator kind of energy value, energy Hamiltonians. Now there is a little bit of algebra, very simple algebra, because to convert this into that form, I need to introduce some change of variables, and these are simply just classical equations still. So I want to write, instead of q lambda, I introduce two new variables. Q lambda is equal to 1 by square root of 4 epsilon 0 v omega lambda square q lambda plus ip lambda. Sorry, omega lambda. Omega lambda, please note, it looks like m omega q plus ip, which we have done for the harmonic oscillator case. So q lambda star is equal to 1 by square root of 4 epsilon 0 v omega lambda square omega lambda q lambda minus I p lambda. I am assuming q lambda and p lambda are real quantities, so I am writing q lambda as a sum of real and imaginary parts with some multiplicative constants, which will actually simplify my expression later on and bring it to a form which looks like that for a harmonic oscillator. So if I now multiply these two, actually I can invert these two equations and calculate q lambda is equal to square root of epsilon 0 v into q lambda plus q lambda star, and p lambda is equal to 1 by I times square root of epsilon 0 v omega lambda square into q lambda minus q lambda star. Just inverting these equations, I can get the capital Q lambda and capital P lambda in terms of Q lambda and Q lambda star. And these are, as you can see here, these are real because there is these are the real and imaginary parts of Q lambda here. So what is Q lambda star? Q lambda star is equal to 1 by 4 epsilon 0 v omega lambda square into omega lambda square q lambda square plus p lambda square. So just multiply q lambda star, I get 1 by 4 epsilon 0 v omega lambda square omega lambda q lambda whole square plus p lambda square. So I can write the Hamiltonian now, replace q lambda star by this, and so the Hamiltonian becomes h is equal to 2 epsilon 0 v sigma omega lambda square into 1 by 4 epsilon 0 v omega lambda square into omega lambda square q lambda square plus p lambda square, which is equal to sigma. So omega lambda square goes off, so I get half p lambda square plus this looks like, this is like this now, p lambda square by 2 plus half what is this? Exactly like a harmonic oscillator Hamiltonian with m is equal to 1, p square by 2m plus half m omega square x square. by defining two new quantities q lambda and p lambda, what I've done is I've expressed the total energy of the electromagnetic field in that volume by in terms of an expression which looks like the harmonic oscillator Hamiltonian. So in this picture, I can consider the electromagnetic field to be made up of an infinite number of harmonic oscillators. Each harmonic oscillator corresponds to one particular mode of propagation of that plane wave. For every value of lambda, I have a harmonic oscillator. Each mode, for each value of lambda corresponds to a different mode. So each mode acts as if it is a harmonic oscillator. There's nothing oscillating, there's no oscillation, there's no mechanical oscillator. But by analogy, formal analogy, it looks like that the electromagnetic field can be considered to be a superposition of an infinite number of harmonic oscillators, and the energy of each harmonic oscillator is half p lambda square plus half q lambda square omega lambda square. So I can write this as actually h lambda, where h lambda is the Hamiltonian for the lambda mode. Now I must make sure, I'll show you that q lambda and p lambda are canonically conjugate variables. And how do I show that? I check whether this h lambda satisfies the Hamilton's equations of motion with q lambda and p lambda as canonically conjugate variables. So what do? I find out, I substitute this h lambda into the Hamilton's equation. So what is the Hamilton's equation? d q lambda by dt is equal to del h lambda by del p lambda. dq by dt is equal to del h by del p, and the other equation is dp lambda by dt equal minus del h lambda by del q lambda. So let me check the first equation. So here is the expression for q lambda. So okay, now I am assuming these operators are time dependent. I have not written the time dependence part here. These operators are all time dependent in the Heisenberg picture. The Hamiltonian is independent of time because it is q lambda star. If you write the time dependence here, exponential minus I omega t into exponential plus I omega t, it is time independent. So these operators are time dependent. In the Schrodinger picture, all these operators are time independent. In the Heisenberg picture, all these operators are time dependent. Well, they will become operators. Right now, they are just classical variables, but q lambda will contain the time dependence. So what is d capital Q lambda by dt? If I use this from here, this capital Q lambda, I will have dq lambda by dt is equal to under root epsilon 0 v. I have dq lambda by dt plus dq lambda star by dt. So dq lambda by dt is minus I omega lambda q lambda plus I omega lambda q lambda star. This is dq lambda by dt plus dq lambda star by dt. So this is equal to minus I omega lambda square root of epsilon 0 v q lambda plus minus q lambda star, and q lambda minus q lambda star can be written in terms of p lambda. So if I substitute for q lambda minus q lambda star, this is minus I omega lambda epsilon 0 v into I p lambda divided by epsilon 0 v omega lambda square. So this is equal to minus I into I is plus 1, omega lambda cancels off, square root of epsilon 0 v cancels off, and I get p lambda. So dq lambda by dt is p lambda. And what is del h lambda by del p lambda? Okay, so where is h lambda? Yeah, here it is. Here is the expression for del h del H lambda by del P lambda is P lambda. Okay, so this is equal to del P lambda. So that is the first equation. Similarly, I leave it to you to show that this H lambda expressed in terms of Q lambda and P lambda satisfy the second Hamilton's equation, implying that Q lambda and P lambda are canonically conjugate variables. So I have expressed this in terms of canonically conjugate variables, and so now I can quantize. And quantization means that I will now write a commutation relation between Q lambda and P lambda. So I will say the commutator Q lambda P lambda is equal to IH cross. And these are now operators. Capital Q lambda, capital P lambda were some classical functions having amplitude and time dependence. There is no space dependence. Space dependence is contained in exponential minus ik dot r and ik dot r. Okay? There is a time dependence and amplitude here. So till now there was no operator, it's all classical functions. Now I say that quantization means having expressed the total Hamiltonian in terms of canonically conjugate variables, so that to show that the total Hamiltonian of the electromagnetic field consists of a sum of infinite number of independent harmonic oscillators. Each lambda corresponds to one harmonic oscillator. So it's an infinite sum of harmonic oscillators of different modes. The Hamiltonian of each mode is given by this, and classically this is the equation. I have shown you that Q lambda and P lambda are conjugate variables, and so I can quantize by expressing a commutation relation between Q lambda and P lambda, and I say capital Q lambda is an operator, capital P lambda is an operator, small q lambda is an operator, small q lambda star, everything is an operator now. It's no more star, it is a dagger operator, and Hamiltonian becomes an operator, vector potential becomes an operator, because remember capital Q lambda is in terms of small q lambda and small q lambda. If these two are operators, this is an operator. If this is an operator, all these are operators, and A vector becomes an operator, because A vector is written in terms of Q lambda and Q lambda star. So the vector potential becomes an operator, electric field becomes an operator, magnetic field becomes an operator, all are operators now. All observables become operators. And when I write this equation, I have actually quantized, and because I know that these modes are independent, Q lambda P mu is equal to 0 if lambda is not equal to mu. They commute. The Q operator and P operator corresponding to two different modes commute with each other. And of course, you have Q lambda Q mu is equal to 0, and Q lambda is also 0, right? There is the commute. In the standard harmonic oscillator problem, you studied one harmonic oscillator, which is defined by position and momentum coordinates, and so a position operator, momentum operator, Hamiltonian operator, etc. Here we have now an infinite number of harmonic oscillators, decoupled harmonic oscillators. They're all independent harmonic oscillators. Each mode is a harmonic, acts like a harmonic oscillator. Complete formal analogy between harmonic oscillator and the electromagnetic field, and the operators representing the harmonic oscillators are Q lambda and P lambda, which will give me what is the corresponding Hamiltonian, which will give me the corresponding electric field operator. All these operators will depend on Q lambda and P lambda operators. So the lambdath mode is now an operator. So this is given by half omega lambda square q lambda square plus half Now, what did I do for harmonic oscillator? We calculated the eigenvalues of the Hamiltonian. So we solved the equation, the eigenvalue equation for the Hamiltonian, and found out the various energy eigenvalues and eigenstates. We can do exactly the same thing now. For every mode, I can find out the eigenvalues and eigenstates. And so, for example, just like we introduced two new operators, small a and a dagger, we can do the same thing here. So I will introduce a lambda operator is 1 by under root 2 h cross omega lambda into omega lambda q lambda plus ip lambda, and a lambda dagger is equal to 1 by square root of 2 h cross omega lambda into omega lambda q lambda minus ip lambda. Q lambda and p lambda are Hermitian operators, just like position and momentum operators for the harmonic oscillator, and a lambda and a lambda dagger, they are not Hermitian because a lambda dagger is not equal to a lambda. They are different operators, and just like we did for the normal harmonic oscillator problem, I can introduce two new operators. In fact, these are related to, in a circular fashion, back to q lambda, because you see q lambda is also written as omega lambda plus ip lambda classically. This is also omega lambda q lambda plus ip lambda. So if you substitute, you can actually show this is the same as the square root of 2 epsilon 0 v omega lambda by h bar into q lambda. But now q lambda has become operators. Small q lambda is related to capital Q lambda and capital P lambda. These two are operators. This is also an operator. And because of the way I've defined, I've introduced some extra factors here, just like we did for the harmonic oscillator, to get an expression for the Hamiltonian in terms of h cross omega. So we have the two operators, the annihilation and the creation operators, and they are defined like this. And so the Hamiltonian, if I substitute this, so if you substitute this and use the commutation relation, what you will get is essentially, what will be the operator? A dagger A plus half into the Hamiltonian operator there was h cross omega a dagger A plus half. And to get this expression, you need to use this commutation relation. In fact, the procedure is exactly the same. Only thing is now you have a subscript lambda here because you're looking at the lambdath mode of electromagnetic wave, of the electromagnetic field. And so you can actually solve the eigenvalue equation for h lambda is equal to, and E lambda will be h cross omega lambda into n lambda plus half. E lambdas are the energies of the lambdath mode. This is now quantized. It is now coming because of the quantization of the problem. What it tells me is the lambdath mode of the electromagnetic wave cannot have an arbitrary energy. Its energy has to be n plus half into h cross omega of that mode. So if I take an electromagnetic wave at certain frequency, say 10 to the 14 hertz, that electromagnetic wave cannot have an arbitrary energy. Its energy has to be h cross into omega of that frequency multiplied by n plus half. It gets discretized now, and this is coming because of my quantization of the problem. Yes, Mohit.
So, over here we are getting an expression which tells us about the quantization of energy values. So,
Of the lambdath mode here. Yeah.
Of a particular mode. So, can this be also reflected as quantization of the omega?
No. Omega is not quantized because the omega is discretized because we have chosen periodic boundary conditions. If I extend the space to infinite, then omega becomes continuous. All frequencies are allowed. If there is no actual physical cavity, if I really consider a laser cavity, for example, then omega gets discretized also because of a classical boundary condition. It's not quantized. So if I consider a laser cavity, what is actually happening is that this cavity will have certain allowed modes. If you take one of those modes, classically that mode can have any energy. But that mode can only have in multiples of h cross omega, odd multiples of h cross omega because of n lambda plus half. This is where the quantization comes in. So if I take I take a cavity or I take electromagnetic wave at one frequency, classically that electromagnetic wave can have an arbitrary energy. This tells me that no, the energies can only be n plus half h cross omega of that mode. It also tells me that you can never have zero energy of that mode. That mode is always there, that there's energy in that mode always, which is the 0 point energy. Like in a harmonic oscillator, the harmonic oscillator can never come to rest. Because if it comes to rest, x is 0, p is 0, you know x and p precisely, and you do not satisfy the uncertainty relation. Similarly, here what is happening is, because of this quantization, you cannot have a situation where the energy of any particular mode is 0. The minimum energy is half h cross omega. So it looks like that there are so the energy can only change, the energy of that electromagnetic field of that mode can only change in packets of h cross omega, which I call photons. Please note that photon is not at one point. It is everywhere. Because this field is supposed to be everywhere. It's a plane wave propagating. And that, the way I've defined this, I've just given a name. Instead of saying that the energy can only be n plus half h cross omega, I say that there are n photons in that mode. When I say there are n photons in that mode, all I mean is the energy of that mode is n plus half h cross omega. And that mode, that energy of that photon is everywhere. This is a photon corresponding to a single frequency that I've taken, because I'll come to more interesting aspects of the photon picture. But so right now what I've shown is that each mode of the electromagnetic wave can only have energies given by h cross omega lambda n lambda plus half. So the total Hamiltonian will be sigma h lambda, which is actually sigma h cross omega lambda a lambda dagger a lambda plus half. And what will be the total energy? Sigma E lambda this is sum over lambda. Lambda goes to 0, 1, 2, 3, 4, minus also there are all possible. Each lambda corresponds to a different mode. And there are infinite number of modes. Each mode has an energy h cross omega lambda into n lambda plus half. So I will say that this electromagnetic field which has this energy has n1 photons in omega 1 frequency mode, n2 photons in omega 2 frequency mode, n3 photons in omega 3 frequency mode, etc., etc. The total energy is given by this. And the each of those modes is represented by a different Numberket. This n lambda which we discussed, which we obtained here, this eigenvalue equation which I wrote for the Hamiltonian operator. Where did it go? Okay, what is the equation satisfy? Oh, here it is. Yeah, this equation. So for each lambda mode, there is an eigenket which is called the Numberket, because it gives you the number of photons or the excitation state of that mode. And so this state corresponds to a ket which is n1 photons in mode omega 1, n2 photons in mode 2, n3 photons in mode 3, like this. So what it implies is h1 into this will give me n1 times this ket. That means this ket corresponds to a state in which there are the energy of the state is n1 plus half h cross omega 1 plus n2 plus half h cross omega 2 plus n3 plus half h cross omega 3 plus n lambda plus half h cross omega lambda plus etc. infinite. There are n1 photons in mode 1, n2 photons in mode 2, n3 photons in mode 3. By photons I mean the number, the excitation state of that electromagnetic field. I could have a situation, for example, that there are no photons in any electromagnetic field, in any electromagnetic mode. What will that correspond to? That will correspond to a state. So this is usually written as this is a shorter form of this, essentially stating that this is a product of these kets corresponding to mode 1, mode 2, mode 3, mode 4, etc. If what is the lowest energy state, what is the lowest state possible when all n lambdas are 0? That is the lowest energy state. And that corresponds to a state which will look like this. n1 is equal to 0, n2 is equal to 0, n lambda is equal to 0, which is usually written as 0 ket. It's like a 0 ket for the harmonic oscillator, where the excitation state was a ground state of the harmonic oscillator. So this is the ground state of the total electromagnetic field. That for all the modes are in the lowest energy state that is possible. Yes, Mohit.
So if you operate the number operator on the state side that you had written.
Now number operator, you have to what is the number operator now? Yeah, because this is only the number operator for the lambda mode, so I have to sum over all the lambdas. So for example, if I operate on this state, so let me operate, so A1 dagger, A1 into psi is equal to A1 dagger, A1, into N1, N2, N lambda. So this operates only on the N1 ket, because this does not operate on the other kets. So I will get N1 So operating with A1 dagger A1 gives me the number of photons or number of the excitation state of the mode 1.
Similarly, it will operate on its respective.
Correct. So what will be the total?
Summation of
because A1 dagger A1 will operate on N1 ket, A2 dagger A2 will operate on N2 ket, A3 dagger A3 will operate on N3 ket. This is an operator, number operator corresponding to mode 1. That number operator operates only on the ket corresponding to mode 1. And that gives me the number of photons or number of the excitation state of mode 1. This N contains a sum of A1 dagger A1 plus A2 dagger A2 plus etc. infinite number. Each one of those number operators operates on the corresponding eigenket and gives me a certain number n lambda. So if you just substitute here and use the fact that this particular operator operates only on the corresponding ket, what you will see is that the total number of photons that is present in the state, the total excitation state of the state of that state. This state, which is the lowest possible energy state, is called radiation vacuum. It's not vacuum in terms of no particles present. It's a state which is the lowest energy state of the electromagnetic field, which means classically there is no electromagnetic field there. But quantum mechanically, please note, this has infinite energy, because the energy of each mode is half h cross lambda, half h cross omega. Half h cross omega 1 plus half h cross omega 2 plus half h cross omega 3, etc. So this gives you an infinite 0-point energy. Actually, there is a problem. It may look as if I can shift my scale and get rid of this. So most of the time we can do it, but this 0-point energy has real effects. The fluctuations in the 0-point energy are responsible for spontaneous emission, light from this lamp. The fluctuations of this are responsible for parametric down conversion, spontaneous parametric down conversion. There are more interesting effects. There is an effect called Casimir effect. If you take two neutral surfaces, they attract each other because of this vacuum field. And this is measured, compared with quantum mechanical predictions, perfect match. So this is not an artifact. It's a real 0-point energy or fluctuations, and we will see that this is what is responsible for the spontaneous parametric down conversion that we have actually discussed a little earlier. Without really from the classical equations, we could not predict the existence of spontaneous emission, spontaneous parametric down conversion. So this is called radiation vacuum, and so there are all the modes of the electromagnetic field are in their ground state. Yes?
In this case, the 0-point energy is infinite, but in classical picture we don't say there exists any.
There is no 0-point energy in classical. No.
I mean, if this energy is infinite, so why do we say in classical limit that there is no 0-point energy? I mean,
No. This is quantum mechanical.
No, sir. I'm just saying that if the energy is infinite,
0-point energy, but I can't draw this energy. I can't draw this energy because I can't go below half h cross omega. So I can't use this energy. I can't use up this energy. If there was 3/2 h cross omega, I can take out h cross omega from there. But if it is half h cross omega energy, I can't do anything. That's the lowest possible state. So I can't draw energy from here. But doesn't mean it doesn't exist. Because if I create a field in that state, I will show you that electric field, there is a fluctuation in electric field. You can see the fluctuations. So if you do a measurement, you will see a measured value. So this radiation vacuum is the lowest possible energy that you can go to when you have, that means it's a state of electromagnetic field where there is none of the electromagnetic wave modes has any classically, you have not excited any of the modes. So vacuum in the sense that it's called a vacuum state in the sense that there is no radiation. You have not excited the radiation. You are in the lowest possible energy state of each of the modes of the radiation field when you are in this state. You can, for example, put one you can go to 3 by 2 h cross omega 1 and you will come to a state. For example, if you can come to a state which is n1 is equal to 1. This will be a state which has an energy of 3 by 2 h cross omega 1 plus, or actually h cross omega 1 plus the infinity.
So, in a sense, every state has infinite energy.
Every state has 0 point energy is infinite. It's always there, all the time sitting there.
After
Yes. So what you can do is you can go from one state to another state by every time adding or subtracting h cross omega corresponding to that mode. Okay. Let me write down some equations which will help us to work out further. For example, if I have a lambda operating on n1, n2, n lambda get, what do I get? Please note, this will only operate on the n lambda part. So I will get square root of n lambda, n1, n2, n lambda minus 1. Yeah. It's the fluctuations, because you cannot have a state quantum mechanically where certain pairs of conjugate variables are precisely known. You cannot have a state where capital Q and capital P, which are becoming exactly measurable simultaneously. So it's a result of uncertainty principle. They're all connected to each other. In a standard normal harmonic oscillator, you cannot have zero energy, because if it has zero energy, the particle is at rest at one point, which means you know its position. It has a precise position or precise momentum, and that's not allowed by quantum mechanics. So there has to be fluctuations, and that fluctuation is essentially contained here, because each mode is like a harmonic oscillator. That means there you can in principle have a state where there is no electromagnetic wave. You have not sent any wave at all. You have not excited any wave, but still there are fluctuating electric fields corresponding to all frequencies all the time. The vacuum is boiling all the time. I don't know whether we can look at the origin of those fluctuations. This fluctuation is being explained quantum mechanically. The mathematical structure explains to me that this must be there, and that is experimentally verified.
all quantum mechanics about this.
Sorry, yeah.
Sir,
Yes.
then we can say the 0 point energy is because of our observation, because by observing this we are disturbing the system, and
No.
that's why it is
Whether you observe or do not observe, there is 0 point fluctuation. See, I am not observing anything. I am trying to find out what are the energy states of my field of one particular mode. Okay, I find that the minimum value is half h cross omega lambda. Whether I do a measurement or not, it is half h cross omega. I cannot. This field cannot have an energy less than half h cross omega when it is in that particular mode. For a harmonic oscillator, the minimum energy is half h cross omega. You are trying to express this by stating that if I try to measure the position and momentum simultaneously, they have to satisfy a certain uncertainty principle, and because of that, that's an explanation. But this contains, the quantum mechanical structure contains the fact. The moment I write the commutation relation, I have already introduced uncertainty principle, because two non-commuting observables will satisfy an uncertainty principle. Delta Q, delta P greater than or equal to h cross y.
we can say that 0 point energy is generated because of our observation, nothing else. Initially, when we don't measure it, it will mean exactly zero energy.
How do you say that? This is what I'm asking. This is what I'm asking. I'm not saying that. I'm saying that whether you observe or not, it is half h cross omega. I'm trying to explain by another way through the uncertainty principle, but it doesn't mean that if I don't measure, the energy is zero. The energy is minimum is half h cross omega. Well, we'll discuss further. Okay, so let me write out the other equations. A lambda dagger, n1, n2, n lambda is equal to square root of n lambda plus 1, n1, n2, n lambda plus 1. Okay, apart from that, you had the A lambda dagger, A lambda operating on this gives you n lambda, etc. So, okay, so this is the, so let me write down the most general state of the electromagnetic field. So, and then we'll solve. So, this is equal to of course normalized. These are all complex coefficients. See, this is a huge state. What it tells me is there are actually infinite summations, and each summation is infinite. That means I can have a state in which the photon number here, in one state there is one photon, one state there are two photons, one state there are three photons, etc. Plus there could be another state in which this n2 can go from 0 to infinity, n lambda goes from 0 to infinity, and this summation itself goes infinite. There are infinite numbers because there are infinite number of modes. The space occupied by the quantum states is huge, and much of it is still unexplored. Because we will go through in the course, we will discuss some very interesting cases, states, one are called as single photon states, coherent states, squeeze states, entangled states, etc. So these are all essentially combination of this kind of combinations, and these are some special interesting properties. Okay, so we will stop here. Do you have any questions? Yeah.
You are relating this 0 point energy to the fluctuations in the system. I don't get it.
Okay. What we will do is we will calculate. I'll take a field which is at the lowest possible state, lambdath mode, for example, the 0 lambda state. That means the lambdath mode there are no excitations. Okay. So I'll calculate what is the average value of electric field in that state. I will get 0. The average of E square will not be 0. So if I have average 0 and E square not 0, there is variance. There is fluctuation. That is what I mean. There is a constant fluctuation of electric fields. The average electric field is 0, but there is fluctuations. There are fluctuating electric fields, there are fluctuating magnetic fields, which is what is giving me finally the energy which I am measuring as half h cross omega. So the fluctuation we will discuss. When I come to fluctuate, I will calculate the average of the electric field, the average of the square of the electric field, and if all the terms are 0, then there is no electric field. But the square of the field has a finite average. That means there are fluctuations. Okay, thank you.